Welcome guys, hope you're doing fine and sorry for the delay in making this video, but I do have something interesting for you this time. So it's a physics derivation and it's about, as you can see here, the time taken for a body in a gravitational field moving towards the source at velocity v0 to move from a distance of r0 to a distance of r1. So basically we have a body over here, and make sure that the body's mass is negligible compared to the source mass, which we're going to be denoted by capital M. And then its initial velocity is v0 and it's towards the source mass, and it is at a distance of r0 from the center of the source mass. And then it moves to a point where it is at a distance of r1 distance from the center of the source mass, and now it has a velocity of v1, which can be easily calculated using the conservation of energy. And now we're going to be finding the time it takes to complete this journey. So first we're going to be defining something called the effective potential of a body, which is basically the sum of the kinetic and potential energy, or basically the mechanical energy, divided by the mass. Basically, it is the energy possessed by a body which has a mass of 1 kg, or basically a unit mass. So basically what we did is we removed the small m terms because it doesn't really matter. The mass is not changing and the energy is also conserved. So due to the conservation of energy of the mass of the body, the ratio will always be a constant also. But this is provided that the source mass does not emit any radiation, which could, like melt or alter the mass of the body. So make sure if there is any radiation emanated by the body, then it should not be altering the mass. So here we're going to be starting with assuming this effective potential and make it the variable k. We're going to denote k as the effective potential. So this is basically the kinetic energy divided by the mass minus gm by r, because potential energy is negative. So the acceleration, the gravitational acceleration, is gm by r squared. So from this we get r is equal to root of gm by a, and then when we substitute the value of r over here, this thing over here, then we get k is equal to half v squared minus root of gma, because imagine putting this here, then you would have root gm on the top because gm and root gm get cancelled, and then the root a, which you have in the denominator of the denominator, goes up, so you basically have root of gma. So basically you have root of gma is equal to half of v squared minus k, because we're going to be taking k this side and root gma that side. Here's where it gets interesting. So gma is equal to half of v squared minus k whole square, and then we're going to be writing a as dv by dt. So because a is like the derivative of velocity over time. So this is the instantaneous acceleration, by the way. So this is the equation we have, and then what we do is we transpose this entire term, the entire RHS, or right hand side, to the left hand side, like we divide it, and then we take dt that side. So basically, as you can see here, we have dt transposed to this side and this entire term down here. And now we integrate both sides. So since gm is a constant, it comes outside, and then the final velocity is v1, the initial velocity is v0, so we just have the upper limit as v1 and the lower limit as v0. And this is called a definite integral because the constant which comes out of integration which gets lost by differentiation, is cancelled because we're subtracting the values. We're subtracting, okay, let's say the integral of this is, let's say, f of v. And then this definite integral signifies that this value is equal to f of v1 minus f of v0. So now what we're going to do is equate this to t, because if you integrate dt, you just get t, because we're basically doing the opposite of differentiation here. So dt becomes t. And then we take this as the time period. Capital T is the time period. Then we're going to be using an interesting integration method, which is called partial fraction decomposition method, or PFD for short. So what we're going to be doing is factoring the denominator, which is half of v squared minus k whole square. So you can write this as 1 by root 2 v minus root k whole square into 1 by root 2v plus root k whole square, because we're basically expressing this as a squared minus b squared form and separating it. And then we express this fraction. This is what we have basically. And then we express it as, basically, these are constants. So we basically express them as the real coefficients into the fraction. So now we just solve for ABCD by, you can basically, you can just take the LCM on the bottom, and then you can just equate the coefficients of all of these. You can equate the coefficients of all of these to whatever coefficient there is on the numerator, and then you'll get the values of A, B, C, D. So these are the values we've gotten by doing that. And then what you do is just substitute these values here. And then these are much easier to solve, obviously. So whenever you have minus 1 by root 8, like we basically took 4 inside, so it becomes 2 root 2. If you apply it to 1 by root 2v, becomes 2 root 2v, and then this just becomes root 2k, because we've taken root 8k cubed outside. And then this is basically a constant, so it comes out again, as you can see here. And then the integral of minus 1 by x is minus ln x. So this is why we have ln of v0 minus root 2k minus ln of v1 minus root 2k, instead of, this term subtracting this term, or basically this term being subtracted from this term. We have the other way around, because we have minus ln of whatever that is. And since you can write ln of a minus ln of b is equal to ln of a by b, that's exactly what we did here. Take that as the first equation. And then this is basically the same thing. This is just v plus root 2k. If you have integral of v plus, like 1 by v plus root 2k dv, then what you're gonna do is just take it as ln of v plus root 2k, because even though you're supposed to differentiate this, like suppose you differentiate this, you're supposed to get this, but then when you differentiate that thing, you're supposed to express this thing inside as a function of the original thing. So you're supposed to differentiate that function also. So for example, v1 plus root 2k is a function of v1, which is inside ln of this thing. So you're supposed to differentiate v1 again after differentiating ln of this thing. So, but differentiating x with respect to x is just 1, so that's why we don't really care about that. And again, since we're subtracting them, we get a numerator and denominator here. We basically get a fraction. That's our second equation. And then when it comes to square, like whenever you have a square of a function in the denominator, then it's just going to be minus of that by just the function itself. And then you just make the denominator by taking the LCM, and then you just transpose this here, then take this here, and then you'll get this. And then as for the last one, which is also the same thing, basically, we just do the same thing because it's just plus instead of minus, and that doesn't really matter. So we just get this instead. And then now we add up all four equations. So here what we're going to do is add up the first two equations first. So we have root 8k cubed as a common denominator, and then when you add these, remember ln a plus ln b is equal to ln ab. So we're just going to basically multiply them. That's what it means. So as you can see here, we multiply them, and we have 3 plus 4, which is equation 3 plus equation 4. Then we get this value. You can verify it if you want. So I'm not really going into the details of how we're going to get this, but it's pretty simple. And as you can see here, we have 2 and 2 here, so we just cancel them out. So we just have this thing left. Now we're going to add both of these two because that's the sum of everything we had so far. And then we're going to take 1 by root 8k cubed common. We're going to take it outside, and then because of that, we have to multiply this into root of 8k cubed, but that cancels out the k we had here, so we basically have 2 into root 2k. So this is the entire value. But then the final equation was gm into integral of all this, so we basically take this into gm. So that's what we have now, this entire value. But this term is a bit confusing, right? It's a bit too long, so we're going to be making it easier this way. So now we know that v squared minus 2k is equal to 2gm by r. We just multiplied the original equation into 2 on both sides. By the way, this is the square of the escape velocity, just so you know. And the second term's denominator can be simplified, like I said. So the constant gm by root 8k cubed can be distributed, because if you apply this here, since this thing is in the denominator here, you'll get gm square at the bottom, as you can imagine. Like, you'll have, this is 2gm by r naught, this is 2gm by r1, so r naught, r1 go up, and then you just have 4gm square, which cancels this out, so you basically have root 2 at the bottom. Root 2 couples with this thing and becomes 4. Root 2 into root 8k cubed becomes, well, 4k root of 4k cubed into 4 again. So basically we have this thing, and then this thing can just be written like this way, and that's all we have. This is the final equation. It's a bit complicating, but it's a very interesting derivation. Hope you enjoyed my video. Thank you so much. Do subscribe for more videos. Bye bye.